Alright guys, today we're going to attempt to prove that one of these forgotten inline sixes that GM stuffed into one of the hardest vehicles to work on might be the modern 2JZ. And we're going to do so with science. So let's go over the basics of the engine. This is an aluminum block, aluminum head, dual overhead cam inline six. And because of the dual overhead cams, they have an extremely stable valve train that is good for 8,000 plus RPM with very little mods. All of the factory timing chain and camshaft related components are very robust. And this is the first engine that GM did variable valve timing on. At this point in time in GM's history, they were just trying to catch up to the Japanese, and the intent of this engine was to compete with the 2JZ. And in general, they are pretty trouble-free, reliable engines from the factory, as long as you change the oil. In general, these engines will outlast the transmissions that were put behind them, and most of the time you will find them in good running condition with an owner who is tired of replacing transmissions. The bore on these engines is 93 millimeters or 3.661, and the stroke is 102 millimeters or 4.016 inches. If you do the math on the displacement, it comes right in around 4150 cc's or 254 cubic inches. One of the things that makes the 2JZ such a great engine is it was sort of built in an era of excess. Toyota had a lot of additional budget, and they could really invest in making an engine that was very over-engineered and very overbuilt for the amount of power that it was making. This is why you see these engines regularly go to 1,000 horsepower on a completely factory engine, and this is how they sort of gained their legendary status as one of the best engines ever built. And today I'm going to try to convince you that this engine right here, which was also built in an era of excess, is similarly capable for most people's goals, and you can do it on far more of a budget. Now, the strong points of a 2JZ include a good oiling system, a very robust block, a decent flowing cylinder head, and stability at high RPM. So let's start off with the block. The block of the 4200 is made with aluminum, whereas the block of the 2JZ is made of iron. Now, right off the bat, you might be saying, well, the 4200 is obviously weaker because it's made with a weaker material. But I tend to disagree. The block on the 4200 exhibits a lot of the same characteristics as the 2JZ has. And if you listen to the experts of the 2JZ, one of the things that they tout as one of the 2JZ's strengths is the cylinder head drains.
As you can see, the 2JZ has a lot more reinforcement. And what these actually are oil return holes. The oil return holes on the 2JZ, as you can see, are outside of the main boundary of the engine block. They have been moved outside for two reasons. Reason one is to leave more material, more meat between the different passageways in the engine block. The second reason and resulting benefit is that they have been used as reinforcement ribs. And the 2JZ engine block is in fact one of the most heavily reinforced engine blocks ever to be manufactured.
And that oil drain is great for getting oil back to the oil pan, but it also acts as a strengthening rib down the side of the block, which stiffens the whole assembly and keeps it from twisting or deflecting, and it keeps your head gasket from having issues. As you can see on the 4200 block, we have those same cylinder head drain tunnels, and in fact they're a little bit larger. Additionally, if we look at the cylinders, you can see that there's a lot of support around the sleeves of the cylinder, and this is also going to promote a more stable head gasket surface and keep those sleeves from moving around any and causing any issues there. Next, let's talk about oiling system. One of the things that makes an RB or a Coyote a little bit of a challenge is the factory oil pump design. So unlike a Coyote or an RB series engine, you don't have to put new oil pump gears in these straight away. And similar to the 2JZ, it's ready to rock as is. Additionally, the oiling system is fairly similar to the 2JZ. You have a main oil galley that runs the length of the engine and feeds all of your mains, and then you have a couple of cylinder head feeds which feed the variable valve timing and lubricates the cam and lash adjusters. Next, we're going to talk about stability at RPM. Now, the 4200 and the 2JZ actually don't share a lot of similarity in the valve train configuration. They're both 4-valve engines and they both have a pent roof style combustion chamber, but beyond that, that's where the similarities sort of end. The 2JZ is a cam on bucket style design, and the cam sort of pushes right on top of the valve. Up front, it has a timing belt, which, depending on who you ask, is a superior design. They say that it isolates the harmonics of the crankshaft from the valve train, but you see lots of guys having success with a timing chain like the 4200 has in very high output applications. I mean, just look at the K-series guys. The 4200, on the other hand, again, it has a timing chain, and we've seen this timing chain have lots of reliability at 8,000 plus RPM. The valve train features a roller follower style setup where it has a hydraulic lash adjuster and a follower, and the cam pushes on that roller follower, and that opens the valve. I believe this to be the more superior setup, in my opinion. Guys have found that the hydraulic lash adjusters are more than capable at crazy RPM, and personally, I'm not a huge fan of a mechanical valve train that you can't adjust easily. The last thing that we're going to talk about in comparison to the 2JZ is the cylinder head. As I mentioned, the cylinder head on a 2JZ is a decent flowing unit. You can shove enough boost into the front of it to make that thing flow, and you can make gobs of power with it. As we move to the 4200, you'll find that it's better in pretty much every way. It has a much larger intake port. The exhaust ports are a little bit lacking, but there's guys making 3 horsepower per cubic inch with one of these engines naturally aspirated. And if you ask the 2J guys, you're not doing that. You're not making crazy horsepower naturally aspirated with a 2JZ. They will dump tens of thousands of dollars into them and they'll make 250 horsepower. And in my opinion, the 4200 cylinder head is already proven to be a far superior unit. So let's go over a summary. You got a block with similar strength. You have an oiling system that is reliable at high output levels. You have a valve train that is good for lots of RPM. And you have a cylinder head that is far superior. The other day I watched this video by the guys over at PRP, and they basically showed the process of how they select a Nissan RB series block for a good engine build. But not all castings are created equally. Some are cast on a Monday, where maybe the workers came in drunk from the weekend, or maybe they were cast on a Wednesday when the workers were finally over their hangover and actually put out a decent product. But how do you determine the strength of the block without cutting it into pieces and doing structural tests on the pieces, which now have destroyed the block that you intended to use? The best way to do that is with one of these. Now we gotta get a little bit nerdy with this and go over some physics of sort of material science and whatnot. Basically, a bunch of nerds a long time ago figured out that for a given material, the harder that the material is, the higher strength that it is. So if we can figure out the hardness, we can reasonably predict some things about the strength. So how do you determine the hardness without destroying it? Well, some more nerds did some tests and found that if you drop a ball bearing on a material, depending on how much energy is conserved, meaning how high does that ball bearing bounce back up, that will give you a very good test as to the hardness of the material. And this video that I watched from the guys at PRP, they showed off one of these, a hardness testing meter. This got my gears turning. And this made me think about, well, could I apply this to what we're doing? Now, the next thing that I'm going to introduce you guys to is tensile strength. Now, tensile strength is given in a PSI number, meaning pounds per square inch. And what it basically means is that you can take a given cross-section of a material and calculate the area of that cross-section. And you can take that PSI, you divide by that cross-section, and that will give you the amount of force that it would take to break the material. So say we had a tensile strength of 34,000 psi. If we had a cross-section of 1 square inch, it would take 34,000 pounds of force to break that material. Now, something that I've noticed over the years of doing research on the 4200 blocks is A356 T6 aluminum has a tensile strength of 34,000 psi. And doing research on cast iron engines that are made out of a material called cast gray iron, we find that they normally have a tensile strength of around 25 to 30,000 psi. Now, if you were paying attention, you probably just noticed that I said that the cast aluminum had a higher tensile strength than cast iron. And I've found that confusing. I've always heard that cast aluminum is weaker than cast iron, and this just didn't make sense to me. After seeing this video from PRP, I came up with a plan. Let's prove it with science. So I did the natural thing of looking up what meter they were using in the video, found that it was around $3,000 to buy one, and then I found the cheap Chinese alternative for $250 on Amazon. Ah, the American way. And this unit that I found on Amazon seems to have good reviews. I found a couple videos of guys using them, but I wasn't 100% convinced of it at that point. And instead I took this thing and I measured a whole bunch of things to see, is this giving numbers that even make sense? Okay, hold perfectly still. Hey, Dad.
Yeah, buddy.
Hold still.
Ow.
579, holy crap.
What did you do to me?
Don't worry about it. All right, so big deal. You can measure the hardness of things. Where are you going with this, Calvin? Well, let me tell you. My goal with testing the hardness on the aluminum blocks for the 4200s is to sort of see if the spec for the A356 T6 even makes any sense. With the material strength spec that they give for the A356, they also give a Brinell hardness number for what that type of material should be. So we used this meter and we did a couple of tests on some 4200 blocks. And we found that they are around 105 to 110 on the Brinell hardness scale. Now, if we look at the material specification, we're seeing that the 4200 block is significantly above that hardness rating. So we can reasonably assume that this is exceeding the spec, and I think we can pretty safely say that it has a tensile strength of around 34,000 psi. But we're not going to stop there. Why don't we test more stuff? Now, some of you might be saying, did you really just say that an aluminum block engine is stronger than an iron block? And you're right to be skeptical, and so am I, because I am probably going to be putting my life on the line to figure out some of this stuff. So we better have our ducks in a row. And I'm definitely more of the kind of guy that I need to see more than just numbers in a book before I'm willing to believe something. So to continue to prove my point, we're going to turn to the LS engine. Now, obviously, the LS came in iron block and aluminum block configurations. And it is a well-known fact that an iron block LS will hold a bit more horsepower than an aluminum block. But I just got done telling you that the way that GM makes their cast aluminum blocks is stronger than the typical gray iron cast iron block. So why does an iron LS block typically last at a higher power level than an aluminum block? And I think that comes down to two things. One, design. If you look at the bottom of the bore on a typical LS aluminum block, you'll notice that there's these little windows in between each of the cylinders. And the main webbing in the block does not tie up into the cylinder portion of the block. Now, iron blocks like this one here don't have that little window at the bottom of the bore, and I think that makes it a significantly stronger design. But that's not the only thing that the iron blocks have going for them, which leads me into the second advantage for the iron block LS engines. And that is that the iron that GM used on the iron LS engine is one heck of a material. I did a hardness test on this block right here. This is an LQ4 block right here, and it tested out at 260 on the Brunel hardness scale. If we look at the material specs for a typical gray iron, this is way off the charts on the hardness, and I also checked a Gen 4 4.8 liter block and found that it was around 250 on the Brunel hardness. Now, remember, hardness means strength in this case. And what that means is that this block right here is in excess of 40,000 psi as far as tensile strength goes. Now the question is, how does a 2JZ block compare to the LS iron blocks? So, let's give it a test. Now I gotta say a huge thanks to my buddy Mike for letting me test his 2JZ GTE engine block. I don't own a 2JZ, so it was nice of him to let me test his engine block. I was happy that it was a turbo block because if anything they should have the highest strength, but we noticed something weird while testing. On all of the other engines that I tested, we noticed that it had very consistent numbers no matter where you measured the strength on the engine block. The 2JZ, on the other hand, varied pretty wildly depending on where you measured it. We saw readings all the way down to 160, all the way up to 227. But I kind of took an average of all the readings that I read throughout the block, and it gave me right around 210. This falls right in line with Class 30 standard gray iron, which has a tensile strength of 31,000 psi. So I think we can safely conclude that the tensile strength of the iron that the 2JZ block was made of and the aluminum that the 4200 blocks were made of are right about the same. So it comes down to design. And if you're not convinced on my discussion on the material strength, I'll add that the Vortec 4200 has a factory main girdle. The 2JZ never came supplied with a main girdle of any type, and it has been well proven that on other engines of similar styles that a main girdle makes a huge difference to the bottom end strength. So my argument is we have a material with a similar strength and the addition of a main girdle. So that really makes you think, is this the modern 2JZ? Some of you are probably leaving comments right now and saying, it'll never have the same aftermarket support as a 2JZ, but I beg to differ. The last thing that we're going to talk about is aftermarket suppliers. Now, all I've ever heard with these engines is they would be a fantastic swap platform if only they had aftermarket support, and I'm getting really tired of hearing this. These engines have aftermarket support, People like the folks at Vortec Performance, who offer turbo manifolds for these engines, and the folks at Atlas Industries, who offer basically everything Atlas, such as shaved valve covers, aftermarket fuel rails, and various other items. The folks at BHJ Damper, who offer an upgraded damper for high RPM stability. The folks at Canformance, who offer coil adapter kits. The folks at Custom Alloy Welding, who offer aftermarket intake manifolds for these. The folks at M-Tech Motorsports, who offer flywheels and adapter plates. The guys at Lime Swap, who offer standalone engine harnesses. The guys at Molnar that offer aftermarket connecting rods. The guys at Schneider Racing Cams, who offer regrind services. The guys at Skunk Works, who offer head porting services. The guys at Snake Eater Performance, who offer drop-in injector solutions. The guys at Stainless Header Manufacturing Incorporated, who offer exhaust flanges. The guys at Stutz Performance, who offer rear sump oil pans. The guys over at True Blue Motorsports, who offer swap kits to put a 6L80E behind these. The guys at 4200 for You, who offer swap kits to put these engines into Colorados. And the folks like my family and I, who offer alternator adapter kits and lash adjuster and shim kits and ignition coil adapters. We all beg to differ with that statement of there is no aftermarket. And I think we'll find as time goes on, this is only going to get better. There are so many options out there for doing these engines in a bunch of different chassis. And frankly, I'm tired of hearing people say, there's no aftermarket. So my advice to you is get one of these engines while they're still widely available and they're still cheap. Because we're gonna keep evolving them and we're gonna keep making them better. And we're gonna keep making high performance parts for them. And eventually, you're gonna have to take them seriously. Let me know what you think down in the comments. I'm gonna end the video off here. Make sure that you like, comment, and subscribe, and we will see you in the next one. Now, one last thing before we end this video off. I'm not a material scientist, so if you disagree with anything that I said about the strength of materials or whether it's even relevant for an engine block, let me know. Is it possible that the modulus of elasticity is a more important metric to look at? Or should we look to the Coyote engines and see them making 3,000 horsepower with an aluminum block and use that as all the evidence that we need? Let me know what your thoughts are down in the comments.